4.6, numerical integration. So we've talked about left-hand sums, right-hand sums, overestimates, underestimates. Now we're just going to talk about two more methods for estimating area under a curve. The first one is the midpoint method. So this is still looking at rectangles. Okay, so the midpoint method is still looking at rectangles. We still have a base times our height, but our height is going to be the x value. We're going to plug the x value of the midpoint of that interval. Okay, so it's still our base times our height, which is the sum of the delta x, the change in each interval, times f of x star. That x star represents the midpoint of each sub-interval. Okay, that's what that represents. Delta x, if we're talking about equal base lengths, then it's that interval b minus a over n, the number of intervals or the number of rectangles that we're looking at. Okay, the next method is the trapezoid method. So with the trapezoid method, well, one, we just have to remember first the area of a trapezoid. 1/2 times the height times the sum of our bases. But this time, if you take a look at kind of, our curve is the red, all right, and the trapezoids are outlined in black. So you can kind of see those. So if we're just going to focus on this first trapezoid here, okay, the bases are going to be these vertical lines, all right, because those are the ones that are parallel to each other. The height is going to be the difference between x1 and x0, okay? So kind of keep that in mind. And h, if we're talking about equal intervals, equal subintervals, h is going to be that b minus a over n, okay? So now if we're looking at trying to find the area underneath this curve using the trapezoid method, okay, our first trapezoid is going to be 1/2. The sum of the bases is going to be f of x0 plus f of x1, and then times our height, okay? Then the area of this trapezoid is 1/2, f of x1 is this base, plus f of x2 being this base, and then our height. And if we continue on, 1, 2, 3, we get to the last one, okay? 1/2 times the sum of our bases. This base is x5, plus the last base is x6, and then times our height. So if we kind of clean this up, we can factor out a 1/2, we can factor out the h, okay? And then what we should notice is as we're going through, we have one f of x0, we'll have two f of x1s because the first trapezoid and the second trapezoid each have f of x1, and continuing on, we'll have two f of x2s, two f of x3s, etc., and then only one f of x6. So again, cleaning this all up, we still have our 1/2 h in front, and then we're going to have two of all of the interior bases, okay? And we'll have one f of x0, that first value of our interval, and one f of x6, the last value of that interval, okay? So all in all, what we're looking at for this trapezoid method, if we kind of clean it up, we have our b minus a over n, that's our h, okay, b minus a over n, but then we have that times 1/2, so that's why it's b minus a over 2n. And then we can kind of take it from there. F of x0 plus 2 f of x1, and we continue on, each of them having 2, and then 2 f of xn minus 1 plus 1 f of xn. All right, so that's using the trapezoid method. Let's get into some examples. This first example wants us to use the trapezoid rule with n equals 4 to estimate the integral from 0 to 8 of the cube root of x dx. And then we'll compare it to the actual value. So first thing, let's go ahead and plot the cube root of x. So as I went through that, all right, nice and easily, we're able to plot the point 1, 1, and we're able to plot the point 8, 2. So the blue is our curve there, but since it wants us to use the trapezoid rule, I just started with 4 intervals, okay, 4 trapezoids essentially. So I take 8, I divide it by 4, and each of my delta x's is going to be 2. All right. So then we go ahead, we can draw in our trapezoids. So that's what you see in red here. Okay. And now what we can do is we can talk about, well, what's x0, what's x1, et cetera, et cetera. So the start, x0 is going to be 0. x1 is going to be 2. x2 is going to be 4. x3 is going to be 6. And x4 is going to be 8. So now let's go ahead and set up the trapezoid method. Use the trapezoid rule. Okay, so we have our b minus a over 2 times n. So 8 minus 0 over 2 times n is 4. Okay, plus f of 0 plus 2 f of 2's plus 2 f of 4's plus 2 f of 6's plus 1 f of 8. And now we just go ahead and we plug in these values, okay? And we get this here, and then from there, I just threw it onto my calculator, okay? So if you have questions from this point on, let me know. If we compare that to the actual area under the curve, right, we're just taking the integral from 0 to 8 of x to the 1/3, and we're integrating it, okay? And we'll go ahead and we'll get 12. So what we can see is, yeah, you should have guessed that this is going to be an underestimate, a lower sum, right, just based off of how those trapezoids are drawn, but we're relatively close. I want you to try this next example on your own. So use the trapezoid rule, n is 4 for that integral, and then we can compare that to the actual value. So first I want you to try graphing it and setting up your intervals. Keep in mind that we're looking at the interval from 1 to 4, okay? And we have 4 sub-intervals, 4 trapezoids that we want. So to figure out what each delta x is going to be, we're going to take our interval, 4 minus 1, divided by n, and we get 3/4. So that helps me go ahead and draw in my trapezoids. So delta x is going to be 3/4. So if I start at x equals 1, and I add 3/4 to it, my next x1 is going to be at 1.75, and I drew that vertical line to represent one of the bases of the trapezoids. Adding 3/4 to that, we're at x2 is 2.5. Adding 3/4 to that, x3 is 3.25, and adding 3/4 to that, we'll get x4 to be 4. Okay, so go ahead and now try to set up using the trapezoid method. Give it a shot. After you have, come back and check how you did. Okay, so we take our b minus a over 2 times n, all right? And then we're going to multiply that by f of 1 plus 2 f of 1.75 plus 2 f of 2.5 plus 2 f of 3.25 plus 1 f of 4. All right, if you go through and you plug this in, these are the values you're going to get, and eventually we'll get our final answer that using the trapezoid rule, we'll get approximately 26.71875. If we compare this to the actual, so integrating this by hand, all right, which we are certainly capable of doing, we would get the actual area under the curve to be 27. So we're relatively close using that trapezoid method. Let's take a look at this third example where we're going to use this table here to talk about the time in seconds and the velocity in meters per second. So what we want to do is we want to estimate the total distance traveled using the table and the trapezoid rule. And we want to assume that velocity is always positive and increasing. Okay, so because of this last line right here, well, first, let's remember what total distance is equal to. Total distance is equal to the integral from a to b of the absolute value of that velocity. However, because they tell us velocity is positive, we can forget about the absolute value of it and just focus on the integral of a to b from A to B of that velocity, okay? Another thing we need to notice is look at our x values, okay? They are not equally spaced out. So this takes into account our height, okay? Remember, the delta x is our height of our rectangles. So this is going to be height 1, right, of that first trapezoid. And so the difference between 0 and 1 is going to be 1, all right? For our second trapezoid, so height 2 is going to be the difference between 1 and 5, or 5 and 1. So that's going to be a height of 4. The height between the third trapezoid, so the third height, is going to be 6 minus 5, or 1. And then finally, for our last trapezoid, the height is going to be the difference between 8 and 6, or 2. So I want you to keep in mind, right? And these values here, the velocity values, those represent the bases, okay? So we can kind of think about it, you know, this is base 1, base 2, all right? And then for the second trapezoid, we have this is base 1 and this is base 2. All right, for this guy. And then for the third trapezoid, this is our base 1, and 5 will be our base 2. And then finally, for our last trapezoid, we have base 1 and base 2. So I want you to give it a try and set this up and see what you get for that total distance traveled using the trapezoid rule. So we have to set them up as separate trapezoids because the heights are all different. So our first trapezoid, that's this information here. We have 1/2 times 1, that's our height, times the sum of our bases, 0 plus 2. Those are the velocity values. Plus 1/2 of our height, which we said was 4, times the sum of our bases. Plus 1/2 times 1, that's our third trapezoid, times the sum of those bases. And then our last trapezoid, 1/2, the height is 2, and the sum of our bases. So when we add this all together, we get 29. We're going to use that fact for this second part of the example. Using our answer from above, so that 29 meters, we're going to estimate the average velocity. Now, one thing we should note, when we see average velocity or something average, we're thinking average value, okay? So average value is our average velocity, okay? So remember, average value is 1 over b minus a times the integral from that interval of that function. Now we're trying to find the velocity, so we're just going to say that our f of x is really v of t dt, okay? So now we can go ahead and use our answer from above because we know that our integral, right, that integral from 1 to 8 of our velocity is that 29 meters. So we're going to use 1 over 8 minus 0 times that integral of 0 to 8 of our velocity, which from above we found to be 29. So then we're able to estimate the average velocity using our estimation from above to get 29 over 8 meters per second. The last thing we're going to talk about is the error formula when we use the trapezoid rule. And we talk about certain intervals. So this is our error formula. You do not need to memorize this, okay? So the absolute value of the error, so that just means the error can come within a certain value, is equal to b minus a to the third over 12n squared times the maximum value of the absolute value of our second derivative, okay? So let's see how this works. So we're going to use the error formula to estimate the error when using the trapezoidal rule on this integral with n equals 4. So they're telling us, okay, if we have 4 trapezoids here, how close are we going to get to the actual value, the actual area under this curve? All right, so step one is I need to know what my second derivative is. So if f of x is 5x squared plus 2, we go through the motion, f prime is 10x, so then f double prime, our second derivative, is going to be 10. So I'm just going to focus on the max of the second derivative portion right now, okay? So let's focus on this. Now, the maximum of our second derivative, the absolute value of our second derivative. Well, since our second derivative is simply a constant, right, the maximum will just be that value, 10, okay? All right, so now we're just going to plug into our formula. We know what b and a are because we're looking at our integral from 3 to 5. So 5 minus 3 cubed over 12 times, we wanted 4, we wanted n to be 4, okay? So that's where we get this guy. And then we said our maximum of our second derivative, the absolute value, was 10. And now it's just a matter of going through and cleaning this up. So 5 minus 3 cubed, and then 12 times 4 squared, 192 times 10, just cleaning it all up. We can go ahead and say the error, the absolute value of the error, is less than or equal to 5/12. So what does this mean? It means our actual area, right, is, let's just say right here on our interval, then using that trapezoidal rule, we can come to within 5/12 of that actual area. That's what this is saying. This last example wants to know how many trapezoids, all right? We're going to use the error formula to find n, which represents the number of trapezoids that we're talking about, such that the error approximation for this integral using that trapezoid rule is less than or equal to this number right here, okay? So if I want to be within 0.00001 of the actual area, I want to know how many intervals are we looking at, okay? So we're solving for n in this case. So I still need to go through and find my second derivative, all right? So cosine of pi x is f prime. Well, the derivative of cosine is negative sine of pi x, but we can't forget about that chain rule. That's where this pi comes from. Then taking the derivative of this right here, derivative of sine is going to be cosine, all right, of pi of x. But then we have to remember the chain rule again, so times pi. So this is where we get negative pi squared times the cosine of pi over x. Now I want to zoom in on this portion right here, okay? Now, negative pi squared, that's just a constant. So we need to talk about the maximum of this guy. Now think about a cosine function and the graph of it, okay? And what we know is the cosine bounces between 1 and -1, right? 1 and -1. And this pi on the inside, that just talks about the horizontal stretch. It is not changing the amplitude. So the highest value, the maximum value we can have of the cosine of pi of x is simply 1. Okay, so we can go ahead and just substitute that. I know the cosine maximum is going to be 1, so what's the maximum, total maximum of that f double prime? That leads us over here, okay? So we have this whole value is f double prime, okay? But the maximum that cosine of pi x can be is simply 1. So then taking the absolute value of that, we get the maximum to be pi squared, okay? So now we're going to go and use our error formula, okay? Only this time we don't know what n is. So we have to solve for how many intervals we're dealing with, okay? So our interval is 1 minus 0 cubed over 12n squared times the maximum of f double prime, which we said was pi squared, and we're going to set that less than or equal to that 0.00001, okay? And so now we're just cleaning it up, all right? And what I did here was I just multiplied both sides by n squared, and then I divided by this value on the right here, throwing it onto my calculator, all right? That's what we did here, and we get 82,246.70, taking the square root of both sides. And remember, we're talking about intervals here, right? Number of trapezoids, so I'm not going to focus on the negative, okay? But since this is, they represent actual intervals, we really have n is greater than or equal to 286.78, but we have to round up because we're talking about the intervals. If we round it down, we're not going to be within that error, but if we round up to 287, we will go ahead and get that error less than or equal to that value that it wanted us to get it to. If you have questions, make sure you ask in class. We'll definitely go over some examples within the homework.